Okay. So I'm going to present our paper on modular software for tessellation as abstract interpretation. So I'm Julien Lepiller, and so in this title there's this word isolation, and there are some isolation techniques that exist. So the first one that we could think of is virtualization. So we have an hypervisor, and it allows multiple OSs to run on the same system while being isolated from one another. But it's a very heavy isolation technique and coarse-grained, so we would like to have something more fine-grained. So in these OS, there run processes, and processes are actually somewhat isolated from one another. They don't have the same view on the memory, and the advantage of this kind of isolation is that it has hardware and OS support, but if you still want your processes to communicate with one another, you still have some costly context switches that you need to make. So we wanted to go one step further. In this process, we are using an isolation technique called software fault isolation, or SFI. In this technique, we have multiple modules. We have a trusted module and some foreign modules. It's a fine-grained sandboxing technique, but it doesn't have hardware support, hence the name software. So this is actually used in real life. So for instance, Google has this NACL thing. It's a way to load plugins in their web browser. So the developer has a software that they want to compile. They use a modified version of GCC that Google provides them, and it compiles to binary code, native code. Then they can distribute it through the store in Google Chrome, and the user can download these plugins. And in that browser, there is a verifier that checks that the binary is actually sandboxed. So there are some modifications that GCC will do to the binary compared to a normal version of GCC. And the verifier just checks that these transformations are present and they are valid. So this transformation that I'm talking about is just rewriting of every address dereference to ensure that any access to memory is actually inside the sandbox. So if we suppose that the sandbox is a part of memory from 0xC0, 002, C0, FF, etc., then if in the original program we would have this memory dereference here, so we want to write this data 0x50 into memory at address contained in this register, then we transform the binary into this write expression. So first we remove the high order bits with this AND, then we rewrite the high order bits with the OR, and finally we do the same write of the same data in memory, but we use this other address. So if before the transformation the write was inside a sandbox, so the address started with C0, then after the transformation the address is still the same, so we have the same behavior of the program. If, however, the write was outside of the sandbox, so an over high order bits, then after transformation the write is inside the sandbox because we have rewritten high order bits. But of course, we will get either different behavior because the address is different, and maybe the program will halt. We have the same exactly the same transformation for reads in memory. So the idea here is that after transformation, the program may have a different behavior, but no write or read happens outside of the sandbox. So usually software fault isolation is defined as a syntactic property, so with these transformations, there is a complex protocol for switching from trusted to untrusted context and vice versa. And there's no formal semantics of it. What we propose in this paper is to define a semantic property of software fault isolation with a more simpler protocol to switch from trusted to untrusted, because we will have a single shared stack and standard calling conventions. And of course, we have a formal semantics for this. So with this single shared stack, we hope that we can improve the speed of our modules. So inside the binary, you would have normally so this trusted module and a foreign module, and each of them would have its own stack. In our proposition, we have a separate stack for all modules. Then each module is actually composed of their data and their code. So we have two separate sandboxes. Usually you would mix the stack inside the data. So any access in the stack is in a data sandbox. So you sandbox stack accesses and data accesses in the same way. But we propose something different. We still have this stack separate. And actually, you don't really know at runtime where everything will be. So every module is not compact. So in our proposition, we want to have some to restrict some rights. So here above in red are the rights for the trusted modules. So we keep all the rights that a process would have on code and data. For the untrusted module, however, the foreign module, we restrict access rights. So for instance, the foreign module cannot write on the trusted data. We have an exception for because the foreign code can call some trusted functions of the trusted code. And that's just for having some communication channel. And then there's an issue with the stack, because we give it read-write access to both modules, and that's not enough for isolation. So we have a dynamic policy that I will explain later. So some examples. Of course, we want the foreign module to be able to call foreign functions. We also want to allow the foreign module to write inside its sandbox. And then, because we don't have execution access on foreign code, on trusted code, the foreign module cannot call a trusted function. So in this paper, we formally study SFI from a semantic point of view. We want to define a verifier as a function-by-function analysis. And we have proved correctness by using standard techniques, so abstract interpretation here. So in the rest of the talk, I will talk about our intermediate representation, how we define the security property, how we design the analysis, and I will finish with a note on the implementation on some experiments we made. So our intermediate language is useful because we work on binary, but assembly code is very difficult to analyze, and it would make a lot of rules. So we use a simpler intermediate language, and that's all there is in this language. So we have expressions that can be a register, and we have an unlimited number of registers. We work on 32-bit integers only, and we can make some operations. The instructions are also very simple. We can assign a value, an expression to a register. We can write or read in and from memory. We have conditional jumps, and we have this halt instruction that suspends execution. So from this language, we have a standard semantics on this language that not very difficult to understand, and we derive a defensive semantics that works exactly like the standard semantics, but it also adds some verification conditions so that it blocks when the standard semantic would have done some unauthorized operations. These unauthorized operations are writes outside of the foreign data or the current frame in the stack, or read outside of the foreign data or the stack, or execution of something outside of the module code or the trusted functions that are the exceptions I talked about. From this defensive semantics, we can express a security property as being an untrusted code is secure if it executes in the defensive semantics either forever or until it halts. So a secure code is never blocked. So here's an example rule for our defensive semantics. So we checked, we are doing we have a small step semantics, so we have an interprocedural context that has some context about the call stack and other things. In the state itself, we have an environment. So we have a representation of this foreign data of the content of the stack after the base pointer. We have a Boolean beta that expresses whether we have already written on the frame during the execution of this function and the current instruction. So here we check that we are executing an instruction that is writing in memory, and these two conditions are just checking that the address we are writing to is actually inside the current frame. So this BP is actually in the context. Another rule is the call rule, which is a bit more complicated. So most of our rules are small steps, but this one is more a closure on the function call. So we still have the same thing as before. So this checks that we have written on the stack. So see here, we have 1 instead of beta. And if that is the case, and we can execute the function until its end, then we can actually make a step to the return address. So we check that in this ellipsis, we check that the last instruction of the function we call is actually a return instruction to the return address. We check that we are calling a function where the stack pointer is below the base pointer, so we are doing the right thing in the stack. And we also check some calling conventions, so the environment are somewhat similar. From this defensive semantics, we can derive an abstraction in a standard manner. So we abstract away all the context and data except for the frame part of it. For the environment and the Boolean, we just use straightforward abstraction. So the environment becomes a map from registers to abstract values, and the Boolean just becomes 0, 1, or top. And the current frame is abstracted by a window around the base pointer. So part of this abstract frame is represents the state of the defensive semantics, and part of it represents the interprocedural context. So here's an example of an abstract rule. So it's the same rule as the first rule I presented before. So we are writing in the current frame. So we are writing in memory, and we check that whatever for some that the address we are writing to, its abstract value represents something like the base pointer plus some offset, and that this offset will always mean that we are in the current frame. So I'm going to explain that just a bit later. So this frame abstraction, I said that we have a window around the base pointer. So on the left is the defensive view of all the stack, and on the right is the abstract frame. So if before we had read and read-write accesses to the whole stack, now we only have read and read-write accesses on a window around it. So now there's a slight issue, because during the analysis we will not know where exactly we are in the stack. So maybe during execution there will be some stack overflow, and we are actually doing some stack operations on, say, the trusted data block. So this is bad. How do we prevent that? So actually we have a proof that in the defensive semantics we can never have buffer overflow. It would not be secure. So what we say is that for every state accessible from the defensive semantics, we have so either if we have written on the stack, then we necessarily are inside the base pointer is necessarily inside the stack. If we have not yet written, then we are either the base pointer is either in the stack or just below it, at most at fs below the stack. So that's what I'm representing here. So if we suppose that we are executing a function and its base pointer is near the end of the stack, then we can have a write to the in the stack, so we can actually call a function. So let's do it. Let's call the function. After calling the function, the base pointer of this of the function that we call is inside this this gray area that is called the guard zone. It's a zone where there is no writes whatsoever, so no read, write, or execution allowed. So any read or write attempt in that will result in a crash. So if that new function wants to call another function, for it to be accepted by our analysis, it needs first to write in the stack. But writing in its frame cannot work because it's actually the guard zone. So writing in it will halt the program. And this can work only if the guard zone is at least twice as big as the frame size in the analysis. So from this we can show that the defensive states are always inside the stack or just below it and never overflow. Then to design our analysis, we have to remember what kind of data we want to analyze. So first we want to have an intraprocedural analysis. So we want our procedures to respect some calling conventions. So basically that's just relations between the environment at the beginning and at the end of a function. We want to ensure also that the stack is written within fs from the base pointer before any of the function call. We also want to ensure that there are sandboxing operations, which are just bit transformations that I presented to you at the beginning of the talk. And we have to check that when we want to read or write data in memory, that we are actually writing it inside the sandbox or reading from the sandbox. And then I remember that we are analyzing binaries, so there's no really distinction between numbers and pointers at this level. For that, we found that the alloc domain for abstract location is a domain that allows us to do most of our work. So basically, this domain is composed of both an abstract region and an abstract offset. So in the example here, we first allocate some data on the stack. So this data is inside the frame region at offset 4, for instance. And then we do some work, and we write 8 at this address. So that's A plus 15. So this address is in the frame region at offset 19. And then this return here will read memory first at address, so inside the frame region at some abstract offset that's between 4 and 13, because we don't know anything about B. So actually, we want to extend that alloc domain with new regions. So we add a region for every register from the architecture we are analyzing to ensure that we are respecting some calling conventions. So calling conventions are actually relations between the environment on the beginning and at the end of the function. So let's suppose that this is the beginning of a function and the end of the same function. We want to preserve the value of EBX. So during the analysis, we first see that we are writing some data that is in the EBX region at offset 0. So that means the initial value of EBX plus 0 at some offset inside the frame region. Then we overwrite the value of EBX with some data. So here we are in the global region, which basically means that it's 0 plus 0x50. And finally, at the end of the function, we read what is at in the frame region at offset 0. And if we suppose that nothing has written at this address, then we will read back this value that is the initial value of the EBX register. So we also want to detect sandboxing operations. And for that, we found that probably the best domain was an abstract bit field. So in this domain, we represent binary data with either 0, 1, or top. So let's suppose that we have this program with this sandboxing operation. So we don't know anything about EAX, so it's in the global domain, the global region, with some top. So here I'm representing 8-bit integers, because 32 bits are difficult to represent in one slide. So the operation becomes, so we remove the higher order bits. So we are still in the global region, but now we know something about the higher order bits. And then with this OR operation, we override the higher order bits to be in the sandbox, and that is detected as, now we know that we are in the sandbox region, so this register is in the sandbox region or some offset that we don't know. But because we still have this 0, 0 at the beginning, we know that it's still an address inside the sandbox. So we have implemented all this. So our implementation is based on Beancat. We have implemented the extended alloc domain that I presented, and we made some experiments to validate the approach. So the experiments are summarized here. So we have some handwritten programs. So those are very short programs, like 20 or 30 lines of code, just to check some verifications. So one of them doesn't pass, and that's the example below. So on the left is something that passes. There's some optimization here. After sandboxing this pointer t, we also remove the low order bits, which means that it's aligned in the sandbox, and every address after that, so there's 16 addresses from this on, are still inside the sandbox. So our analyzer is able to detect that. So it can accept this kind of program where we don't sandbox every access. We only sandbox it once, and then we can write in this array. On the right side, however, we have exactly the same program, but written with a loop. It does the same thing, but it's not accepted because we don't refine on guards, so it doesn't see that it stops at the right moment, and it rejects it wrongly. Then we also have unwritten incorrect programs to make sure that our implementation is correct. They are all rejected, so that's good. And we have used the sandboxing compiler to compile some bigger programs, so from a few hundred to a few thousand lines of code. So we could analyze 10 of them, and they all passed, which is good also, because it means that we can use a compiler to compile things that we are able to accept. So in conclusion, we have formalized SFI as a defensive semantics with a shared stack, which allows optimizations and to have standard binaries, which is not the case in the standard SFI models. We have designed an analysis that is derived from with standard techniques. We also have a proof of correctness. So if we analyze and it is accepted, then it doesn't block. And we have defined an extended version of the alloc abstract domain. On the implementation side, we have some encouraging experiments, because the time it takes to validate all these programs, even the longer ones, is for most of them below a few hundred milliseconds, and only one of them takes above 1 second, so it takes 3 seconds to validate one of them because of nested loops. So what we want to do now is to simplify the defensive semantics, because there are some redundant information in there, but that means that we have some more proof efforts to make. We could extend our work to multiple modules, which would bring our definition closer to what is done in reality. And there's no conceptual difficulties here. We could also extend it to have multiple threads. So here there's no existing formal treatment of multiple threads in SFI. We are pretty sure that it's feasible for an interleaving semantics, but we don't know yet if that's feasible for something better than an interleaving semantics. We could make some improvements in the analysis, so like the non-passing example that I showed you before. If we could refine on quads in our implementation, then it would pass. And we also are unable to identify switch statements in binary code. So any switch in the original program would fail the verifier. So thank you for your attention.
Yeah, so in the analysis of the stack operations, right? So from what I understood, the idea is that you want to make sure that the untrusted code doesn't access stack outside of the untrusted frames, and then sometimes you cannot do this, right? Obviously, because you cannot always do this. So do you have some sort of fallback technique for these cases, so that or you have to reject the if you fail to prove correctness of stack operations, is there some fallback technique that you can use to modify the binary, or you just have to reject the program completely?
So our work is focused on verifying a binary that is given to us. So we don't really, we haven't really worked on modifying the binary itself.
All right.
So we just reject something that doesn't follow our conventions.
Yeah. Thanks.
So I've been wondering what domains you are using in your abstract interpretation. For example, you did not analyze the guard, which would require just linear constraints of some sort. But you probably need to do some analysis of arithmetics, or do you?
So the idea with the guard zone is that the defensive semantic cannot go past it. It would halt before it goes past it. So when we abstract this defensive semantics, we know that the concretization will only in the concretization, the base pointer will only be in the stack, and it cannot be after or before the stack. Did it answer your question?
Partly. I think we can take it offline.